Hello APC Mechanics students, today we'll solve the past paper FRQ 2007, exercise 2. In March 1999, the Mars Global Surveyor GS entered its final orbit about Mars, sending data back to Earth. Assume a circular orbit with a period of 1.18 times 10 to the power 2 minutes, its equivalent in seconds, and orbital speed given by the following. The mass of the GS is 930 kg and the radius of Mars is the following. Now we need to calculate the radius of the GS orbit. So here, notice carefully that the orbit is being perfectly circular. So we can use anything that is related to perfect circles. We need to find the radius. We have the time and we have the speed of the GS. So we can determine the radius, which is basically the distance. And because the speed is constant, we can say that speed is distance over time. Now here, because the time which is given is the time related to circular orbit, which is the period, referring to a distance which is the coverage of a circle or a circumference given by 2 pi r. Then we're interested in determining the value of r. Now isolating for r would be given by vt divided by 2 pi. The speed is given by 3.40 times 10 to the power 3. Multiplied by the period, which is 7.08 times 10 to the power 3, divided by 2 pi. Now plugging that expression on the calculator, we would have the radius along which GS is orbiting Mars is given by 3.83 times 10 to the power 6, and the SI unit of distance is meters. Now, although here they have mentioned in the text that we have Earth, but the two bodies that we're interested in is basically the GS and the Mars. Now, we're asked to calculate the mass of Mars. What does this mass represent? Is it the central mass or the orbiting mass? Because the GS is orbiting Mars, then Mars is the central mass. And we know that because we have the speed, the central mass is related to the speed by the following formula. But remember, this is an FRQ. We cannot use this formula from scratch. We need to derive it, and it's not found on your paper sheet. Then apply Newton's second law. That is given by F naught is equal to ma. Now we're applying this law to the moving mass, which is the orbiting mass. So that would be the mass of GS. Now what are the forces acting on GS? The pull of gravity from Mars on it, which is Fg, equals to ma. And now we can say projection along the centripetal direction. Now the pull of gravity requires no projection because itself acts along the center. And the acceleration would be the centripetal acceleration. Now the pull of gravity would be given by the coupling constant g, the orbiting mass, the central mass divided by r square, and that would be equal to mv square divided by r. Now here we can start applying the cancellation effect. M with m cancels, and we would end up having gm divided by r is equal to v square, and we're interested in finding m. The small mass is the orbiting mass, the big M is the central mass, and we have everything. Then if you isolate for the central mass is given by v square multiplied by r divided by g, which is equal to the speed is 3.40 times 10 to the power 3 to the power of 2. Now r is given by 3.83 times 10 to the power 6 divided by g, which is the gravitational constant or the coupling constant. Now g is not found in the exercise itself. It is found on the first paper of your exam, and it's given by 6.67 times 10 to the power minus 11. Plugging that expression on the calculator would have a value given by 6.64 times 10 to the power 21 kg. And notice carefully, if you compare the value of the masses, this is of the order of 10 to the power 21, and this is just 930 kg. Always the central mass is much heavier than the orbiting mass. Now in part C, we need to calculate the total mechanical energy of the GS in this orbit. So always and whenever, it is even much more important than if you're applying the conservation of energy. If you need to calculate the total mechanical energy, you need to specify your PE level precisely. And in masses that are coupled due to gravity, the PE level is taken to be at R is equal to infinity. Then let me say take PE, take the PE level, to be at R tends to infinity, which means the gravitational potential energy between the two planets is negative. Then E, the mechanical energy. Now here, no need to specify apply conservation of energy, simply because we're calculating the mechanical energy and we're not applying any conservation law. Then take the PE level to be at infinity. The mechanical energy is given by kinetic and the gravitational potential energy. Here, although we have two bodies, we have the central mass and the orbiting mass, but the only body admitting kinetic energy is the orbiting mass, and it's given by half mv square. Now the gravitational potential energy is negative because both bodies are being bounded by distance r, which is less than r tends to infinity. So the two bodies are below the PE level, and it's given by minus gm m divided by r. Now that would be capital R. Here in this case, we have all the values for mv and r, and as well as for the central mass, but we can do some computations, substitutions that make our calculation easier. Already we know that v square can be replaced by this expression, which is gm divided by r. Minus gmm divided by r. So notice that here we can factor out both gmm divided by r, and we would have half minus 1, so that would be minus half gmm divided by r. Although I'm repeating again, this step is not important. You can simply calculate the mechanical energy from here, and that would be minus half the value of g is given by 6.67 times 10 to the power minus 11. Now the small mass is the mass of GS, which is 930. The central mass is given by 6.64 times 10 to the power 21. And the orbital radius is basically given by 3.83 times 10 to the power 6. Now plugging that expression on the calculator, the mechanical energy is given by a negative value, which is minus 5.38 times 10 to the power 9 joules. Now in part D, they're telling us if the GS was to be placed in lower circular orbit, closer to the surface of Mars, would the new orbital period of the GS be greater than or less than the given period? I would directly tell you that it's less than, and this can be directly indicated from Kepler's law, because we know that for Kepler's law, the period square is proportional to r cube. So when r decreases, the period would decrease. Okay, so let me state it. According to Kepler's third law, T square is proportional to r cube. Then as r decreases, then t decreases as well. Now for the final part of this exercise, in fact, the orbit the GS entered was slightly elliptical with its closest approach to Mars at 3.71 times 10 to the power 5 meters above the surface. Now here there are two things that are very important for us. Elliptical means that the orbits are not circular anymore and these relations break down. The other thing is that they're measuring the distance with respect to the surface, and this is very important. We know that one trick always appears related to distances. Whenever we're using relations related to planetary motion, R is the center to center separation distance and not with respect to the surface. So now let's continue. That would be the closest with respect to the surface and its furthest distance, which is this much, above the surface. Now if the speed of the GS closest approach is given by this one, so this speed would be associated with this one. So if this is R1, that would be V1, for example. This is R2, and for sure we're asked to calculate the speed at the furthest point, which is V2. Now before we proceed, let's determine R1 and R2, and let me say these are not R, however this is H1 and that would be H2. Then R1 in this case would be H1 plus capital R that we have determined previously. Now although capital R have been determined using the fact that this is completely circular, but R is a constant. Once it has been determined from a certain condition, it won't change. Then H1, which is given by 3.71 times 10 to the power 5, plus R, which is 3.43 times 10 to the power 6, that would give us 3.8 times 10 to the power 6. What does this distance represent? It is the closest distance along its orbit, and R2, which is given by H2 plus R. Now R2 would be 4.36 times 10 to the power 5, and R is fixed to be 3.43 times 10 to the power 6. Plugging that on the calculator, we would have 3.87 times 10 to the power 6, and as you can see, the difference is very small. For this reason, we need to take few decimals. And now we can apply the conservation of angular momentum. We know that the angular momentum for a body orbiting a central mass is always conserved, so the angular momentum 1 is equal to angular momentum 2. Although we have a force, there is a force acting on GS, but it produces no torque. So the net torque is 0, which means the angular momentum is conserved, which means I1 omega 1 is equal to I2 omega 2. Now GS is considered as a particle, and its angular momentum is given by mr1 square. Omega 1 is given by v1 divided by r1, and the angular momentum for the second point, the difference would just be in r and v. Then that would be mr2 square multiplied by v2 divided by r2. Now here they would cancel. The same for the mass, which means that r1 v1 is equal to r2 v2. And remember that this relation, we can use it directly in an MCQ but not in a free response, and we're interested in determining v2. Then v2 in this case would be given by what? Would be given by the fractional expression r1 v1 divided by r2. Therefore v2 is r1, that is given by 3.8 times 10 to the power 6, multiplied by v1, which is 3.4 times 10 to the power, let me double check, I think 3, or here from the exercise itself, 3.4 times 10 to the power 3, divided by 3.87 times 10 to the power 6. Plugging that expression on the calculator, we would find that the new speed at the furthest location is given by 3.34 times 10 to the power 3, and the unit of the speed is meters per second. And that's it for me in this video, guys. See you soon in a new one.